We're going to take a look in this video, continuing our investigation into probability, into the question, how can tree diagrams help calculate probabilities? And first, before we get really into it, we're going to first introduce the idea of the tree diagram, which basically is a diagram that has a branch for every decision. So for example, let's say I have a bag with 3 red marbles and 5 blue marbles. And I'm going to draw 2 marbles out of the bag without replacement. In other words, I draw 1 marble out, look at it, and then I draw another marble out. To set up what's happening here with the tree diagram, what we'll do is we'll have a branch to represent every decision or every possible outcome. So first I go in and I grab my first marble. The first marble could be either red or blue. The probability that it's red is going to be drawn on the red branch. There are 3 out of 8 red marbles. The probability that it's blue is written on the blue branch. There are 5 out of 8 blue marbles. But then a second thing happens. We draw again. And as we draw again, coming off, I could draw red initially and then a red again, or a red initially and then a blue. Or coming off the blue option, after blue, I could draw red, or after blue, I could draw blue. Now, the probabilities on these second set of branches is going to change, because going down the left side, if I drew a red the first time, there's only 2 reds left out of 7 total left in the bag for the second draw. Similarly, if I draw red on the first draw, there are still 5 blues left, but only 7 total in the bag. Going down the next branch, if I go blue then red, if blue was the first draw, there are 3 reds left out of the 7 that remain in the bag. But if blue was the first draw, there's only 4 blues left out of 7 to draw on the second draw. What's nice about a tree diagram, though, is it gives us an easy way to calculate all the possibilities. Notice the first branch is a red, then red. The second branch is red, then blue. The third branch is blue, then red. And the fourth branch is blue, then blue. We can quickly calculate the probability of any one of these outcomes by multiplying down the branch, because really it's an and probability, red and red. So we'll do 3/8 times 2/7. And let's go ahead and make it a decimal. 0.1071 is the probability of getting 2 reds. 3/8 times 5/7 gives us 0.2679 is the probability of red then blue. Going down the other direction, blue then red, 5/8 times 3/7 is also 0.2679. And blue, blue, 5/8 times 4/7 is 0.3571. And now I can see the probability of any single outcome. And then we can use that tree to help us calculate various probabilities. For example, if I want to know the probability that both are the same, both are the same color would be either a red, red, which has a probability of 0.1071, or a blue, blue. So we'll add the 0.3571. That gives us a total probability of 0.4642 that both marbles are the same color. We could calculate the probability that we get no reds. No reds only happen in one place, and that's the blue-blue situation. That's the 0.3571. We could calculate the probability of at least one red. Now, this is interesting, because I could combine at least one red. We could combine the 1071, the 2679, and the 2679, because all three of those have at least one red. Or another way we can get there is to use the complement. We know all four of these are going to add to 1.0, or 100%. And we can subtract off the stuff we don't want, because there's only one thing we don't want. We don't want blue-blue. So that's 0.3571. And when I subtract, we get a probability of at least one red of 0.6429, or 64.29%. So you can see these tree diagrams can really help us identify the pieces we want in the probability questions. One question we're very interested in, though, uses what is called Bayes' theorem. Bayes' theorem helps us calculate conditional probabilities. We already know that the probability of A given B is equal to the probability of both, the probability of A and B, divided by the probability of the given information, the second part. But we can rewrite that denominator in another way that actually allows us to find opposite conditional probabilities. We'll keep the same numerator, probability of A and B. And B doesn't really care what A does. It's really a combination of the probability of B given A plus the probability of B given not A. Whether A happens or A doesn't happen, both of those together give us that probability of B for the denominator. And that formula actually helps us build what's called Bayes' theorem. Now, your textbook looks at Bayes' theorem using a table method. If you want to see a table method of attacking Bayes' theorem, you can look at your textbook. But I actually prefer to do Bayes' theorem with a tree diagram. Let me show you what it looks like. Let's say a detective agency employs 3 detectives. Aaron, Betty, and Claudia. ABC. Aaron is assigned 30% of the cases and solves 20% of them. That means of the ones he assigns, he solves 20% of the ones he's assigned. Not 20% total, but 20% of the 30 he was assigned. Betty is assigned 45% of cases and solves 15% of them. Claudia is assigned 25% of the cases and solves 35% of them. So a lot of given information in there. If it's assigned to Claudia, she'll solve this percent. If it's assigned to Betty, she'll solve that percent. If it's assigned to Aaron, he'll solve that percent. Let's say a case is solved. If a case is solved, what is the probability it was solved by Claudia? We're not actually going to use the formula for Bayes' theorem. We're going to set up a tree diagram to help us work out the idea behind Bayes' theorem. And as we set up our tree diagram, the first branch represents what happens first. The order is important. So first, a case needs to be assigned to a detective. It could be assigned to Aaron. It could be assigned to Betty. Or it could be assigned to Claudia. Let's give percentages to each of these. Aaron is assigned 30% of the cases, so 0.3 for Aaron. Betty is assigned 45% of the cases, 0.45 for Betty. And Claudia is assigned 25%, 0.25 for Claudia. Depending on who it's assigned to, one of two things is going to happen each time. It will either be solved or not. Solved or not. Solved or not. And we can put probabilities on these based on our information. If it's assigned to Aaron, Aaron solves 20% of his cases. So Aaron solved is 20%, which means the not solved must be the rest of them. Well, 20% and 80% will make that 100%. So subtracting from 1, we find out the not solved has a probability of 0.8. Betty solves 15% of them. So Betty solved is 0.15. Not solved, subtracting from 1, is 0.85. Claudia solves 35% of her cases. So Claudia solves 0.35. Subtracting from 1, her not solved is 0.65. We know from our tree diagrams to figure out any individual result, we're going to multiply down the branches. So Aaron solved 0.3 times 0.2 is 0.06. 0.3 times 0.8 is 0.24. 0.45 times 0.15 is 0.0675. 0.45 times 0.85 is 0.3825. 0.25 times 0.35 is 0.0875. And 0.25 times 0.65 is 0.1625. These are our options. Now we're ready to answer the question, since we've organized the information in our table. We want the probability that it was solved by Claudia, given it was solved at all. Starting with the given, because the given means we ignore everything else and we only look at the given stuff. We're given that it's solved. Well, there's 3 places on this table where we see solved cases. Once under Aaron, once under Betty, and once under Claudia. That given information is going to become our denominator. Our total solved is going to be 0.06 plus 0.0675 plus 0.0875 to get the total probability of a solved case. That goes underneath what we're actually looking for. We're looking for Claudia's solved cases. Specifically, we're going down the Claudia branch and the solved branch. The part we're most interested in is when that 0.0875 happens, that 0.0875. So you see our Claudia and solved both go in the numerator, and the denominator is made up of all the given pieces, all the solved pieces. If we add those together, we get 0.0875 divided by 0.2225 to get a probability of 0.3933. If this case was solved, there's almost a 40% chance that it was solved by Claudia. That is how Bayes' theorem works. Now, the most useful application of Bayes' theorem actually comes out of medicine. So let's do another example in medicine that is one that you might be more likely to see. The idea behind Bayes' theorem in medicine is that quite often we have to give a test to a patient to see if a disease is present or not. The problem is the test is never 100% accurate. Sometimes the test says you have the disease when you don't. Other times it says you don't have the disease when you do. So just because you get a positive test doesn't mean you have the disease. And if you get a negative test, it doesn't mean you don't have the disease either. Bayes' theorem helps us understand what the probability is you actually have the disease or don't based on your results. Let's look at a specific example. Let's say a disease occurs in 2% of the population. A medical test has a false positive rate of 8% and a false negative rate of 3%. Before we get to the question, let's organize this information in a table, make sure we understand what false negative and false positive mean. As we make our table, the first branches need to represent what happens first. The first thing that happens is either the patient has the disease or they don't have the disease. So let's make a branch to represent they have the disease and a branch that represents that they don't have the disease. We know this disease occurs in 2% of the population. So the probability of getting the disease is 0.02. The probability of not getting the disease then, subtracting from 1, is 0.98. Now they go in the doctor's office and they take a test. The test is either positive or negative. They go in the doctor's office and they take a test. The test is either positive or negative. Now, to help us out with the identifying, let's also add the words true and false here. If you have the disease on the left, the correct true diagnosis would be a positive test. A true positive means you have the disease and you got a positive. The negative would be false or incorrect. So a false negative is going to be on the second branch here. If you don't have the disease on the right, a true result would be negative, that you don't have the disease, which means the false positive is that third branch there. By getting everything labeled, it's going to help us when we see a false positive rate of 8%. That's the false positive branch of 0.08, which means the other half, subtracting from 1, must be 0.92. The false negative rate of 3%, false negative is the second branch of 0.03, and the true, subtracting from 1, is 0.97. Now we can multiply down the branches to see all the possibilities. 0.02 times 0.97 is 0.0194. 0.02 times 0.03 is 0.0006. 0.98 times 0.08 is 0.0784. And 0.98 times 0.92 is 0.9016. We're going to ask 2 questions with this diagram. The first question is going to be to find the probability that a person has the disease given a positive test. You go to the doctor and say, do I have this disease? You take a test. The test says positive. Yes, you do. What's the probability you actually do have the disease? Well, with Bayes' theorem, we look at the given positive and focus our attention on the given positives. Where are the positive test results? There's a positive test result on the left, and also the third branch represents a positive test result. That's your given. That goes in the denominator, 0.0194 plus 0.0784. We want to know who has the disease. So tracking the disease, that's going to be this number on the left, the 0.0194. So when we add, we get 0.0194 divided by 0.0978. The probability you actually have the disease is 0.1984. In other words, you have less than a 20% chance of having the disease, even though you had a positive test result. That becomes very interesting. Now we'd have to do further tests to see if you actually have the disease or not, because there's an 80% chance you don't have the disease. Now, granted, it's a lot more than it was when you walked into the doctor's office. Before the test, there was only a 2% chance. But given the positive test result, that 2% has grown to over 19% chance. But what about the opposite case? What's the probability that you're healthy given a negative test result? If the test says you don't have the disease, what's the probability you actually don't have the disease? Well, now what's given to us is negative. So we focus our attention in the table on the 2 negative values, and those become my denominator, 0.0006 plus 0.9016. The numerator is what I'm looking for, that I'm healthy, that I don't have the disease. And if I track don't have the disease, that's the 0.9016 option. So when we add those together, we get 0.9016 over 0.9022, which means we got a 0.9993 chance that we're healthy, given that negative test result. Those are pretty good odds. In fact, they're better than they were. When you walked into the office, there was a 98% chance you were healthy. The negative test result makes that grow up to a 99.93% chance that you're healthy. That's looking pretty good. That's Bayes' theorem, using the table to build the denominator out of the given, and the numerator is the part we're looking for. Go ahead and try a few of these on the homework assignment, and let me know if you have any questions.